The PDB Reader is a required module whenever your builder workflow involves a protein structure. It provides the essential first step for preparing a protein or protein ligand complex prior to system construction. In this demo, we introduce the advanced options of the PDB Reader. Since there are 14 options in total, which can be difficult to explain all at once, we will instead present examples to illustrate each option in detail. We have already demonstrated the basic usage of the PDB Reader in a previous session. Here we will begin from step 3 to highlight the advanced options. If you need instructions on the basic functions, please refer to the earlier demo first. In this case, we will load the 5ZK9 PDB, which contains the human eukaryotic translation initiation factor, EIF4E, bound to a hydrocarbon stapled peptide. In this dataset, chain A corresponds to EIF4E, and chain B corresponds to the stapled peptide ligand. After loading the PDB, the blue highlighted options are automatically activated. By default, 4 options are enabled, and we will additionally enable the mutation option manually. 1. Chain selection. The PDB file includes 2 protein chains and water molecules. It also contains a heteroatom as MGP. To validate the structure, click Validate Structure. After reviewing, click Apply to add the ligand to PDB. For water chains, select appropriately. We will deselect these options. 2. Model missing residues. The PDB Reader can automatically generate missing residues in each protein, and most options are suitable by default. However, note that modeling more than 10 consecutive missing residues may result in an inaccurate structure. In this PDB, residues 207 to 210 are suitable for generation. You can keep the default selection. 3. Non-standard amino acid, RNA substitution. If the PDB contains non-standard residues, this option will be activated by default. For residues that are not supported by PDB Reader, you have to generate their force fields in the same way as a ligand. Force field generation is only supported for amino acids. In this case, since the default option is Generate FF, the program will automatically generate and apply the force field parameters. However, you should still validate the structure because the generated parameters may not always be accurate. After clicking Validate Structure, review the structure carefully. Once confirmed, click the Apply button. 4. Terminal cappings. In this option, terminal capping is applied by default. If you want to generate a cyclic peptide or protein, you must select cyclization. In this case, however, you may choose neutral caps, charged caps, or apply custom caps depending on your modeling needs or the force field requirements. Here, we will keep the default selection. 5. Phosphorylation State. Although serine 209 is phosphorylated by MCK1, 2, this residue is missing in the structure. Since residue 209 cannot be recognized, we will instead add phosphorylation at serine 82 as SP1 manually. By enabling this option, you can represent the phosphorylation state. 6. Peptide stapling. Peptide stapling is a method of chemically linking 2 residues to stabilize the peptide structure, often preserving an alpha helical conformation. This improves structural stability, binding affinity, and sometimes cell permeability. In this case, we will connect residue 31 and residue 33 in chain A, using the Meta 4-patch manually. This will introduce a staple and help maintain the desired conformation. After setting all the options and clicking Submit, the generation begins. This process takes some time. Once the generation is complete, both the existing peptide stapling and the standalone ligand are displayed. By downloading the file, you can further confirm the peptide stapling you manually added using any PDB viewer program. This PDB can then be used for various studies such as MD simulations or free energy calculations.